So let us continue for the third part. Okay, in this part we will review briefly the programmable logic controller, the PLC, and the difference between the regular PLC and a safety PLC. Okay, as we have already mentioned, the PLC deals with two kinds of signals, the sensor signal and the actuator signal. This is a typical an architecture for a regular PLC. We have here X is the inputs, okay? And we read X and we store them in I. I is an image, okay? Why do we store the input in an image? Because we need to have a stable, suppose that this image is saved and the controller works using this image. And we are having a memory, okay? And as you see, these arrows explain the flow of the information. And we have what's so-called the Q. The Q here, as it's mentioned, it is the image of the output. The output is mainly the signal to the actuator. Okay, this is the image, and then the image is transported to the output Y. This is the idea in a nutshell. Okay, the PLC operates in what's so-called scan cycles. What's the scan cycle? It is described, the scan cycle is that we execute get I, and then the PLC program operates, and then we execute put Q. Get I reads the input and stored it to the image, and put Q reads the output from the image and communicates it to Y. As is mentioned here, the values of the output, the image ensures that the data is available to the program is consistent. Consistent means that it doesn't change, because we read the data at an instant of time and it is possible to change. So simply to avoid this, we put it in the image and make sure that we are working on that. Okay, one full scan cycle typically takes few milliseconds. It is expected that these few milliseconds will be suitable for many industrial operations. These are two scan cycles: get, run the controller, and put, get and put. So the cycle, as you could see, is being repeated. Now this is the regular PLC, it's done. What about the safety PLC? For the safety PLC, we need to split, as you could see here, this is the safety PLC with the yellow highlights. We need to split the inputs and we need to split the outputs. The architecture here, as we see, it's almost we are having two PLCs. The safety PLC and the regular PLC. As you could see, we have here two images for the input and we have two images for the output. We execute get IR and put and get and put, and we execute the program. As you could see here, we are having the memory and controller, and we are having, this is called the data buffer for communication between both of them. I would like you to pause right now and see whether the upper layer or the regular layer and the lower layer, the safety layer, are symmetric or not. I would like you to try to pause the video and think about that. If you pause, you will see that, for instance, this IR can communicate to CS and IS can communicate to CR, so it's almost symmetric, and IR to CR, IS to CS, this is symmetric. Okay, QR puts in YR, QS puts in YS, this is symmetric. The same for the memory, the same even for the data. However, the asymmetry is between CR and CS and QS and QR. CS can give orders to QR. CS can give orders to QR. However, CR cannot give orders to QS. CR can just read what is in QS, but it cannot give orders. Okay? This is, as we see, this is like, this is why safety is having stronger influence, okay, stronger authority, more priority than the regular PLC. This is the idea behind safety itself. So this is the safety PLC in a nutshell. And to clarify further, this is the scan cycle. Okay, the scan cycle operates on the safety part and then on the regular part sequentially. Okay, so this is in a nutshell, this is the safety PLC. Okay, and the one question is how to do this splitting for the XR and XS, YR and YS. Here each component is subscripted R. the additional component XS. XS and YS are the safety input signals. This XS and YS are determined based on the standard that have been mentioned before, the IEC 61508 standard. So the engineer working to design the PLC should identify which inputs are needed within the IEC 61508. Okay, so at least we can identify XR and XS. What about QR and QS? We will deal with this later. Okay. When a discrepancy, I believe that's all. He will not. I believe this is enough for the safety PLC. Now we can have a look at the preliminaries. Okay. The preliminaries. First of all, he is describing what's called the plant. Please make sure to discriminate the difference between this scripted P capital and unscripted P capital. This symbol is not this symbol. Okay, we are having this extra mark here. Okay, so P here is the set of P's. Okay, and we have also a set I of what's so-called Boolean input variables. If you have a look at the videos that I have described related to another paper, you may understand what's meant by a Boolean input variables. I believe these are simply the sensor readings. Okay, so a component is a finite automaton. A finite automaton, either P1 or PM, is defined as a 5-tuple of L. L is the set of locations or the states, if we are going to use the same notation used in the textbook. And what about sigma? Sigma is the set of events. What about this arrow? This arrow, it is a subset of L product sigma product L. This is the transition. Okay, he didn't want to complicate and to describe what's so-called a transition function. L node is the set of initial states or initial locations, and the LM is the set of the marked locations which denote safe locations. We always try to reach safety. The event set can be partitioned into two sets, the uncontrollable events and the controllable events. Okay, most probably the uncontrollable events will be related to the sensor readings, and the controllable events will be related to the actuator signals. For all FAS P, again, don't get confused. P is not the set of all P's. P is one of these plants. For a specific plant, we define a function called location P and event P. Location V lists all the locations or all the states of P, and the event P lists all the events of P, all the segments. That's all. Okay, and the elements in I model the variables of the input image, and this I is the Boolean input variables, and these variables, as we know from the input image, are mainly the sensor readings. Okay. Again, this paper is following the paper that we have described in another video, and for the Boolean input variables, they convert them into their finite automata. A Boolean input variable is either false or true. Okay, these are the two states, and it is either on or off. These are the two events. F on T, and T on F are just a description of these transitions. Okay, F is the initial value, and FT are the market values, and as you see here, the market values are highlighted. Okay, and since the sensor reading is uncontrollable, he is using a dashed arrow. If the event is controlled, he will use a solid arrow, but we don't have any controlled events here. That's why we don't have any solid arrows. What's somehow confusing with this paper is how the requirements are defined. Okay, in the paper that we have described in another video, the requirements were defined using, and even in SuperMecha, the requirements are defined using an automaton or automata. Here, the requirements are not defined using automata. The requirements are defined as a set. This is a scripted capital R. It is not that this R. this symbol is not, or this symbol is not like these symbols. Each one of these requirements are, the scripted are the set of requirements. Each one of these requirements is defined by a two tuple. The first element is sigma, which is an event. Okay, and the C is a Boolean condition. C is a Boolean condition. C is not just a Boolean input variable. It's not a BIV. It's not an element in I. It's a Boolean condition. Okay, what's the meaning of a Boolean condition? He is defining the Boolean condition here, that we're using this long notation. Okay, it is defined as a specific grammar. I will not go into these details. Okay, the condition will be somehow a complicated condition. Okay, for any condition we can operate on the condition using a location and the BIV. The location returns the set of locations, okay, that are referenced here, or the set of states, and the BIV returns the set of all Boolean input variables that are mentioned here inside this place. Okay, fine. What about supervisor synthesis? He is just reciting what we know about safety, what about controllability, what about non-blockingness, and what's so-called maximal permissiveness. Maximal permissiveness means that the supervisors imposes the minimal restriction on the system to satisfy safety, controllability, and non-blockingness. Okay. Again, for the supervisor implementation, suppose you have got the supervisor. He is again describing that the variables of the input and output have to be connected. The question is how to implement that. Okay. For connecting the variables in the input image, the Boolean input variables are already defined, as we could see here, are used. The variables of the output are modeled by the set Q. Okay. For connecting these variables to the supervisor, so-called hardware mapping is supplied. A hardware mapping TQ denotes the relation between an event and a value assignment to a variable in Q. Formally, this is TQ. It's a subset of event multiplied by an output multiplied by a B. B is a Boolean value or true or false. For instance, is getting us an instance of TQ. We are having in sigma Q and T that belongs to 2Q. This defines that when event sigma occurs, the value T is assigned to Q, okay, where Q small is an element in Q capital. That's all. Okay. To generate an algorithm, the control code or the PLC code, there are algorithms available in what's called the CIF toolset. The algorithm is based on what's called linearization procedure. All this is out of the scope of the paper. This is not the scope of the paper. The scope of the paper is how to synthesize a supervisor that should be split. Okay. Okay, I will stop here. And in the next section I will describe how did he implement the splitting.